Hi everyone. In this video, we will first look at Green's theorem, which is a special case of Stokes' theorem in two dimensions. We'll first see how Green's theorem falls out of our statement of Stokes' theorem that we saw at the end of the last video. We will prove Green's theorem, and then we will see how we can use Green's theorem to actually help us prove the full version of Stokes' theorem. So to begin, let us just remind ourselves what the statement of Stokes' theorem was. So the first several sentences give a lot of setup, but the fundamental idea of Stokes' theorem was that if I have a nice surface S that's bounded by a nice curve C, then the surface integral of the curl of a vector field F over the surface is equal to the line integral around C of the vector field F. Okay. Now, you'll notice here, again, there are a lot of conditions. Many of these deal with the fact that we have this parameterized surface, and so we want to be able to say some things about the parameterization R of R, which maps T to the surface S. We need to say some things about that region T in the parameter space, as well as its boundary, which we call capital gamma. So we need to have sort of all of these conditions be satisfied. But under these nice conditions, we get Stokes' theorem as stated here. So the first question we want to ask ourselves is, what happens if we apply Stokes' theorem to a surface S which lies entirely in the xy plane? So the situation we want to imagine here is we're sitting in three dimensions, but now our surface S is just some subset of the xy plane. Okay, so you can imagine I just have S that's sitting in this plane that lies sort of exactly parallel, exactly perpendicular with the board here, right? Just coming out of the board. Okay, so this is the S I want to consider. Well, if I imagine that this surface S is, say, oriented in the boundary of S, which we call C, is oriented in the counterclockwise direction, then the normal that is compatible with that, so I think about a right-hand rule, so I curl my fingers in the direction of the parameterization, my normal would be pointing this way. Now, if I think about a unit normal to this surface, well, this set S lies entirely in the xy plane. So my unit normal must point straight up. And since it's a unit vector, right, this vector actually has to just be, right, k, 0, 0, 1, right? It's the unit vector pointing straight up in the z direction. And that's true at any point on this surface, right? So if I'm over here, it's still the same normal vector, right? So let's think then, right, if we think about Stokes' theorem or just the formula that comes out of it, right, we get that the surface integral of the curl of F ds is equal to the line integral over the boundary C of F d alpha. Well, if I think about what's going on here, right, the definition of this, right, I'm sort of dotting this with the normal vector, but the only thing that's going to survive here, right, if I take a dot product of the curl of F with a normal vector, right, the only thing that's going to survive here, my x and y components of my normal vector are both 0. The only thing that's going to survive is the z component, okay? So if I just sort of write out, you know, what all of this is, right, I get that this is equal to the double integral, right? So now it's just going to be an integral. I'm just thinking of this in like the parameter space, but the parameter space is just the xy plane, right? So this is going to be a double integral. And what I'm going to be left with is the z component of the curl of F. So if I think about what curl of F is, right? Normally I write out this inner product, or sorry, this not inner product, this sort of determinant form. And then if, right, we generally assume that we have our vector field F, right, in terms of its components, P, Q, and R. But the only thing I care about here is the zth component, because that's the only one that's going to survive. So if I look at what the zth component of that will be, it will simply be, so normally, right, you get something times I minus something times J. And what I'm interested in is what do we get as the zth component? And that's going to be dq dx minus dp dy. Okay. And so if I come up here in this integral, what I'm going to be left with is just dq dx minus dp dy dx dy. So again, this is now a double integral. Right? It's no longer, I don't even think about it as a surface integral because now this set S lies entirely in the xy plane. And now if I look over here and I think about what's happening here on the right-hand side, well, here I have a line integral. So if I think about some parameterization of this curve C, right, the parameterization or any parameterization you take of this, right, it might be, say, we'll call this alpha sub x of t, comma, alpha sub y of t. So this is just the x component of alpha, the y component of alpha. But then the z component of this curve, it lives entirely in the xy plane. It will just be 0. So when we go to think about what this actually is, right, then the way we normally think of this line integral is this should be the integral of f of alpha of t. Sorry, it's no longer a. The integral of f of alpha of t for whatever t varies over. Say t is between a and b. This would be the integral from a to b of f of alpha of t dotted with alpha prime of t dt. But if I think about what's going to happen here, right, that's the z term is going to be a 0. Okay, so what I'm going to end up with here is like an integral from a to b of, I can think of this as the x component of f evaluated at alpha of t times alpha sub x prime of t plus the y component of f evaluated at alpha of t times alpha prime or alpha y prime of t. But then if I go to do the z part, the derivative of this with respect to t will be 0. So that term will disappear. And you end up with this, which, what is this? Well, this is really just the line integral of f. Sorry. We have a name for these components, right? The x component of f is just p. The y component of f is just q. And so what you really have is just the line integral of q dx, or sorry, of p dx, plus the line integral, or sorry, just we usually don't write this again, just write plus q dy. Basically, you just ignore the z component because there's not going to be any z component here, right? And so what we end up with this being equal to is we get that this is a line integral. And now I can just think of this in the xy plane of p dx plus q dy. Okay. And now this gives me a perfectly good formula, right, that just works in the xy plane. Okay, this is the special case of Stokes' theorem that we will refer to as Green's theorem. So anytime, right, we have a surface that lies entirely in this xy plane, we can reduce it to this. And in fact, you could do it in any plane, right? This would, if your surface lies in any plane, you could still repeat this. You would just your variables would be slightly different than just immediately being x and y. But because they're dummy variables, you could just switch them to x and y at the end. All right. So let's look at, we have to remember that Stokes' theorem does have conditions. So many of those conditions are going to get passed on to the relevant pieces in Green's theorem. So I do want to put up, one nice formal statement of Green's theorem. As soon as we can get this erased. All right. So again, we need conditions on many of these things. So for example, we need P and Q to be scalar fields that are continuously differentiable on some open set S in the XY plane. We need the boundary of S, which we call C, to be a piecewise smooth Jordan curve. And we want to let R be the union of C and its interior, right? So that R with R being contained inside of S, right? So again, the set where these are differentiable, right? Basically, we're making sure that these things are differentiable on R, right? And I'm sorry, I think I misspoke. So C here is the region. C is the boundary of R, right? And so we end up with a double integral over R of dq dx minus dp dy is equal to the line integral p dx plus q dy, where again the line integral c is taken, the line integral is taken around c in the counterclockwise direction. That corresponds with the fact, right, that we were using that unit normal pointing up. Right? Of course, if you wanted to do it in the other direction, right, you could have just swapped that. If you wanted the curve to be oriented in the clockwise instead of the counterclockwise direction, you would just negate things appropriately. All right, so what I want to do is I want to prove Green's theorem, right? We haven't proven Stokes' theorem. So what I've really just shown you is that, well, if Stokes' theorem is true, then Green's theorem is true. But we haven't proven that, so we really haven't proven Green's theorem yet. So let's just prove Green's theorem first. And let me point out that it suffices to prove the following two formulas. So what I want to do is I want to show that at least on a certain type of region, and we're going to look at a region which is both type 1 and type 2. But if we have a region that is both type 1 and type 2, then both of these formulas must hold. If both of these formulas hold, then if I add them together, right, on the left-hand side, I would get a double integral over R of dq dx minus dp dy. And on the right-hand side, I would get an integral, a line integral of p dx plus q dy, right? So I would exactly recover this formula that we see here. So again, another way to think about this is I am showing this equality by showing that essentially the integral of this piece matches up with this piece of the line integral, and this piece of the line integral, right, matches up with this piece of the double integral. And that's really what I'm going to do. Now, I'm going to do it for a nice type of region. So I'm going to do this for a region which is both type 1 and type 2. Okay. It maybe not surprisingly, I'm going to use the sort of type 1-ness of the region to help me here, and the type 2-ness of the region to help me here. Okay. All right. So let's get started. So the first thing we want to do, we will assume, well, we're not really assuming because we said this is what we're proving it for. Okay, so let's let R be type 1. Okay, well, what does that mean? That means then my region R, what does it mean to be type 1? It means you're the set of points x, y that can be written in the form say a is less than or equal to x is less than or equal to b, and your y values are bounded between some functions of x. I'm going to just call those f of x and g of x. Okay. Okay. Well, now let's start by looking at one part of the double integral. Okay. So if I look at the double integral over r of minus dp dy, okay, dx dy, I can actually compute this by iterated integration, and I can do it in either order. So I actually want to do this iterated integration first with respect to y, and I'm going to pull the negative all the way out for the time being. I'm going to integrate first with respect to y. Well, my y values range from f of x to g of x. And then with respect to x, and those values range from a to b. All right. Now, I'm going to move this negative back inside the first integral of these iterated integrals here, and then I'm going to use that negative sign to flip-flop the order of integration, the limits of integration here. So this will actually be equal to the integral from a to b of the integral from g of x to f of x of dp dy, dy, dx. Okay. Now, if I look at this, I first want to compute this inside integral here. But what do I need? I need to take the antiderivative of dp dy. Well, that's just p, right? It's just the function p of xy, right? So this should be p of xy evaluated at f of x and at y equals f of x and at y equals g of x and take a difference. So this comes out to be an integral from a to b of p of x comma f of x minus p of x comma g of x dx. Okay. And now I'm going to stop there, right, for this particular integral. Okay. So also, let me look at the other side of this. So what I want to do, and I'm going to sort of draw a picture off to the side here. So let me imagine that I want to look at the integral of p dx. Okay, so think about this region. It's type 1, so roughly I can think of it as, right, the region looks something like this. So this function down here is f of x. This function up here is g of x, right? This is x is equal to a. This is x is equal to b. Okay. Now, I need to think about this line integral. I'm thinking about it going in the counterclockwise direction. So it's oriented in this way. And what I want to do, if I look at these, there's really like 4 parts of this whole boundary, right? So let me sort of label them. I'll call this one C1, C2. I'm going to move in a counterclockwise direction for labeling them, C3 and C4. So if I'm interested in thinking about the integral of p dx over C, then really that ought to be the integral of p dx over the curve C1 plus the integral, plus the integral of p dx over C2. So I'm just using the fact that I can break up this line integral over parts of the curve, plus the integral over C3 of p dx, plus the integral over C4 of p dx. All right. Now, immediately, if I sort of think about what's going on here, along these two sides, okay, what ought to be happening? So if I think about this side, where I have C2, okay, C2 could be parameterized as what? It could be parameterized as alpha of t is equal to b, comma, So my x value is b. Now my y value, what, is going to run from f of x up to, or sorry, from f of b up to g of b. So I could parameterize that by something, okay? It wouldn't take a lot of time. But what I want to point out is that if you parameterize it in this way, then alpha prime, this is going to be 0, this is going to be non-zero. So when you move along C2, there is no change in your x component. Okay? This portion of the integral will be 0. Similarly, over here, you could parameterize C4, right, as a comma some function, but the x component of the derivative will be 0, and so this piece of the line integral will be 0. So what you're left with then is the integral over C1 of p dx plus the integral over C2 over C3 of p dx. Well, let's think about what parameterizations for C1 and C3 look like. So they're actually so C1 is fairly straightforward. You can parameterize it as t comma f of t, right, for t values going from a to b. Now, C3 is a little harder because you want to do the same thing, but then you need your x values to run backwards, right, from b to a. So instead, what we can do is I'm going to call this C3 bar. It's going to be t comma g of t, and I'm just going to understand that this parameterization, since it's running in the opposite direction, is going to give me negative what I want here. So if I parameterize C3 is the same curve, just running in the opposite direction, I can parameterize it as t g of t for t going from a to b. And so now each of these line integrals, right, I can evaluate. This simply becomes the integral. So what is it? It is p evaluated at alpha of t. So this is p of t comma f of t times alpha prime of t, but it's just the x component. Well, that's just 1, so times 1 dt, and this is for t values going from a to b. Now remember here, C3 is running in this direction. We have C3 bar. So really what we're thinking about here is we're going to do negative the line integral over C3 bar. Okay. And so here what we have is we're going to get a minus. Again, this parameterization goes from a to b. And now it's p of alpha of t, so t comma g of t, times alpha prime of t, but just the x component. So that's just 1 again. Now notice here, t is just a dummy variable, so I could change it to anything, and I could collapse these integrals, and I would get the integral from a to b of p of x comma f of x minus p of x comma g of x dx. And now we notice that this is exactly the same expression we got up here, right? And therefore, we have that this is equal to this. Okay. So this is the first of those two formulas that we want to establish. Okay, so we get this by using the type oneness of the region, essentially. Okay. Now, it turns out that you can repeat this for essentially the Q terms by, well, just doing exactly the same thing, but you use the type 2 bit. Okay, so I'm not going to write out sort of every detail, but let me just sort of show you how you might go about modifying what we already have here. So now we're going to use the fact that R is type 2. Okay, that really just means what? It really just means my y values are bounded between a and b, and now my x values are bounded between functions of y. Okay. So again, the sort of general picture we would then draw for this is something that looks like this. Got f of x, got g of x, and then got b and a. Okay. Now the first thing, now here I would look at, instead of minus dp dx, I would look at minus dq, sorry, instead of minus dp dy, I'd look at dq dx. Okay, I would write this as an iterated integral. I wouldn't have this negative sign. Okay, I would write this as an iterated integral of dq dx. But now I've got to take care of this. Actually flips the order of integration. I'm going to flip the order of integration. And this is now from f of y to g of y. Okay. Now, again, what's going to happen here? So here we're going to have the antiderivative of, sorry, so this is, we sort of actually just don't need this intermediate step here because there's no negative sign to bring in and flip things around. So what's going to happen, I'm going to take an antiderivative of q with respect, of dq dx with respect to x. So that's just going to be q. And so I'm going to end up with this piece being q of y comma g of y minus q of y comma f of y, and now this is dy. Okay, this is exactly the same idea, you're just dealing with a slightly different term. Okay, now over here we need a q dy. We're going to break it up into all its parts. Okay. Now, to save myself a little bit of headache here, let's see. So this will be q dy. This will be q dy, q dy, and q dy. Okay. So let's see. Now I need to label things over here, and to save myself some headache, I'm going to label them in a slightly different way than I did before. Let's see. Let's call this piece. Call this curve C1, C2, C3, and C4. Okay. So it's the same idea as before. Along C2 and C4, your y values aren't changing. So the derivative of alpha with respect to the y component of the derivative of alpha will be 0. So both of these will end up being 0. So you'll just be left with this q dy. Oh, I guess I was using red for my changes. So let's stick with that. So you end up with this q dy and q dy. Okay. Now again, we're orienting everything in a counterclockwise direction. And so you get the same thing as before in this direction, right? You're fine, right? You can parameterize this as t comma g, g of t comma t. So this curve C1 now, right, can be parameterized as, the problem here is that these should be functions of y, right? Okay. So I can parameterize this as g of t comma t for t going from a to b. This I have to do the same thing where I'm actually going to parameterize it going in the opposite direction. So this is f of t comma t. And it's going in the opposite direction. So that's why we pick up that minus sign. And then by virtually an identical argument, I'll just sort of skip to the punchline here. It really is an identical argument here. Down here, you'll end up with and I'm sorry, I've made a mistake up here. I'm realizing now this should I've flipped these around. This should be g of y, y, and this should be f of y, y, right? So this is q of let's see. Again, we're evaluating here. We evaluate the antiderivative, which is q, when x is equal to g of y, right? So this is g of y, y, and then this is f of y, y. Okay. And now down here, when we do this, we'll get q of q of f of y, sorry, of g of y, because that's the one that goes with C1, g of y, y, minus q of f of y, y, d, y. All right. So then we have established that, right, these things are equal, okay? And now we've proven both of those formulas, which added together give us Green's theorem. Now, the last sort of note to make here is that we have proven this for regions that are both type 1 and type 2. And you might sort of worry that, well, maybe most regions aren't type 1 or type 2. And indeed, I guess most of them aren't. But we want to fall back on something we fell back on earlier with things about double integrals, which is while we may not be able to write every region as a type 1 or type 2 region, we can decompose nice enough regions into regions that are all either type 1, that are all both type 1 and type 2. So just to sort of again give you the essence of that. So again here, now the idea is if I have, some sort of strange region in the plane, right, I can start decomposing this. So I could, for example, sort of make a cut here. Maybe, let's see, I'll make another cut here. Let's assume, just to not make this too complicated, we don't have to change it to too many things. So I think all of these regions are both type 1 and type 2. Now, again, the picture we sometimes draw in our heads is that the flat sides tell us whether it's type 1 or type 2. And if that is something you really feel strongly about, you could even subdivide this even more. I mean, that's the nice thing about a lot of these. You can just sort of keep subdividing them until you just sort of get rectangles everywhere. So, or almost everywhere. So now you can sort of see, if I look at this region, for example, okay, I could think of this as a type 1 region where my lower piece is here and my upper piece is actually just this point here. And then it's bounded on the left and the right by functions. Sorry, that would be, I guess, a type 2 region. If I think about it, bounded by constants on the top and bottom, left and right are bounded by functions. But I can also think about it as being bounded on the left and right by constants, and then bounded on each side by these functions. Okay, so this region is both type 1 and type 2. Okay, I can play a similar game here and here and here. This is just a rectangle, which is easy to see that it's both type 1 and type 2. So as soon as I show that it works for regions that are both type 1 and type 2, it works for more general regions that I can decompose into sort of, I can sort of partition into subsets that are both type 1 and type 2. And then what you do is you apply Green's theorem on each of the pieces. Okay, so if you think about what Green's theorem says, so you apply the double integral on each piece. Well, the double integral on each piece, when you add it all together, gives you the double integral over the whole region. That's good. But then you're also going to do you're going to do line integrals around each piece. So you imagine you do the line integral here, and then let's say you come over here, you do the line integral, and let's see, that's in a counterclockwise fashion. Then you come over here and you do the line integral in a counterclockwise fashion. Okay. Well, notice you did the line integral when you applied Green's theorem on this region. You did the line integral in this direction. When you applied it here, you did the line integral in this direction. You computed the same line integral in opposite directions. They will cancel out. When you compute the line integral on this region, right, those will cancel out. When you compute the line integral on this region, those will cancel out. When you compute the line integral on this region, right, these will both cancel out. Okay. And so the only things that survive, if you'll notice, are the line integrals that are moving in the counterclockwise direction around the boundary of the whole region. So again, you can then just prove Green's theorem for these more general regions by applying it on each of these subregions once you partition your region into subsets that are all type 1 and type 2. All right. So great. Now we've proven Green's theorem. But that still doesn't necessarily immediately show us that Stokes' theorem works, right? We know that given Stokes' theorem, Green's theorem is sort of a corollary, but now we've proven the corollary, which doesn't tell us anything about this more general theorem that we might like to prove. Okay, so again, let's go back here. This is the formula that we would want to establish for Stokes' theorem. Okay. Now, what we're going to do first is we're actually going to think about, we're actually going to prove this in a way by applying Green's theorem to a couple of different pieces. We're going to prove this in a similar way, which is we're going to say, well, if I could prove these three things in this case, then if I added them all together, that would give me Stokes' theorem. Okay. But in order to do that, what makes this a little hard is there's not sort of clear pieces of this here. Okay, so what we want to actually discuss first is a little bit of some alternative notation for surface integrals. So before we delve into sort of using that specific surface integral of the curl of f, let's just think a bit about, like, what if I just have the surface integral of any vector field, right? Well, by definition, right, we know that this is like a double integral over some region T in the parameter space of f of r of uv. So this r of uv is like the parameterization of the surface. And then dotted with the fundamental vector product dr du cross dr dv. And then this is like du dv. Okay, so again, this is actually how we just define the surface integral, all right? All right, but again, we want a slightly better way of expressing this. So what if I imagine that f has components? So what if f, the vector field, right, has components p, q, and r, right? Okay, and so if I do that, so now I'm thinking of that in terms of its components, I might say, well, I want to think about this in terms of its components, right? What are the components of this fundamental vector product? Well, one of the things we showed back when we talked about this is that we could actually express this fundamental vector product, right? We could actually express it in terms of its components, but its components were these weird sort of, they're actually, each of them is a determinant of its own little matrix. Okay, so the x component was dyz duv, the y component was dzx duv, and the z component was dxy duv. So these were the components of the fundamental vector product, where, and again, you could go back to the video, but like just to remind you, so like dyz of duv, so this was the determinant of dy du, dz du, dy dv, comma, dz dv. So this quantity dy dz over du dv was just defined to be the determinant of this. So it was dy du times dz dv minus dz du times dy dv, right? That's just how those are defined. And again, that comes out of just writing out all the terms of this cross product, right? And here, also I should mention, right, that where are these x, y, and z coming from? They are coming from the parameterization, right? So the parameterization R has components capital X, Y, and Z. Okay. All right, so using all of this information now, though, we can express this dot product, right? So if we come back to this main equation here, right, then this really ought to be equal to what? I can break it up and write this as a double integral over t of, okay, let's do x components first. So it would be p, right, of, sorry, let's see, p times this dyz duv, and then that would be du dv. Then I could do the y components, so that'd be another double integral of t over t of q dz x duv, du dv. And then finally, a double integral over t of r and dxy duv du dv. And now if you sort of stare at this, you start to feel like this is almost playing a role like that line integral of q dx plus, of p dx plus q dy in Green's theorem. Okay. And so what we do is we, in a way, right, this is really trying to isolate out the sort of yz components of this integration, right, but leave the x behind. Here, this is trying to leave out the y stuff. Here, this is trying to leave out the z stuff. So we actually just define each of these pieces in their own way. So this is like a surface integral, but instead of integrating it with respect to all the variables, you're really just sort of doing it with respect to y and z. And so we would write this as the surface integral of p, but then we would write dy wedge dz. Okay. Now, the reason for this notation is beyond the scope of this course. It really gets into some more sort of manifold theory type stuff, or there are higher, generalizations of Stokes' theorem that apply in more general settings. And so that's where this notation is coming from. But here it's really just denoting, for our purposes, that I have the yz piece here. Okay. Plus, then I would get a surface integral of q dz wedge dx plus then a surface integral of r dx wedge dy. Okay. So each of these things, we're just defining these things to mean this. Now, why is this helpful? Well, it's helpful because it makes the notation a little less messy. Okay. So this is just an alternate way of sort of writing out. Again, all we're really writing out here is the is exactly this surface integral. We're just expressing it in a slightly different way. In particular, we're expressing it in terms of the components of the vector field. Right? Okay. All right. So how does that help us then when we go to prove Stokes' theorem? Well, for one, it actually is going to make sort of explaining how we want to break this up in order to prove it substantially easier. So just as we did with Green's theorem, we're going to do this by saying, well, I want to prove these three things, and then if I prove all three of these things, then I'll be done. Because then I add them together and I get what I want. So I want to prove the following three things. So notice that what I'm doing here is I'm really just taking the components of the line integral, so the x, y, and z components of the line integral, but now I'm breaking up this into some different pieces. Now, it's a little hard to see here exactly what's going on, but if you look at, for example, look at the pieces over here that have dx wedge dy. So if you notice, if I add these two together, I'll get dq dx minus dp dy, dx wedge dy. Well, dq dx minus dp dy is the z component of the curl of f. Okay. Similarly, if I look at dz dx, right, the dz wedge dx terms, so I get them here and here, this is going to give me the y component of the curl of f. The dy dz terms, if I add them together, give me, and sorry, this should be a capital R here. Okay. But this will give me a dq dz plus dr dy. Right over this maybe. Capital R. Okay. So this will give me the x component of the curl of f. So if I prove all these things, add all the things together on the left-hand side, right, then on the left-hand side, I just get, I think about just sort of summing all of these things up. What I'll end up with on the left-hand side is just the line integral of f d alpha. And on the right-hand side, what I will end up with is I will end up with the surface integral of the curl of f ds. Okay. So if I can prove all three of these things, then I will have proven Stokes' theorem. Okay. All right. We are going to walk through the proof of the first one. Okay. And just as we saw with Green's theorem, the others are fairly similar. But we want to walk through this proof, and what I will do is I will put up a fully sort of teched out version of the full proof, right? So you don't have to, guess about it. But what I would suggest you do is watch what we do for this first one, see if you could repeat it for Q and R, and then you can go check and verify that we actually get the same thing. All right. So I've sort of outlined it here, so we'll just sort of go step by step. So we want to prove this. Okay. So the first thing I'm going to do, right, is I'm going to express my parameterization. So just call R of UV is going to be, it's going to have components X, Y, and Z. And then what I first want to do is I want to convert the surface integral. So over here is the surface integral. I want to convert this to some double integral over T. Okay. So what is that going to look like? So if I just think about going back, right, I'm really just saying, what does this mean in this notation, right? So we get that the double integral over S of this minus dp dy, dx wedge dy, plus dp dz, dz wedge dx. Okay. So what does this really mean? Well, it really means, right, by definition, I'm going to integrate over t. So for this part, I'll get dp dy. And then this is just going to be times that dxy duv, and then I'll get a du dv. And for this term, I'll get a double integral over t of dp dz, and then times this quantity dzx over duv, du dv. All right. Now, the next thing we're going to do is we are going to write this lowercase p of uv. It is going to be p. So remember, p is the x component of my vector field f. But now I want to evaluate that along the surface. That's essentially what this lowercase p of uv is going to be, capital P, but evaluated along the surface. Okay. So what we can do then is verify that the integrand, right, this integrand right here. So I should note, right, these are both integrals over the same region. So I could just combine them into one integral. Step I forgot here. So it's just this whole integral. And then what we want to do is verify that actually if we define P in this way, we actually get that this double integral over T of dP, oops, I've gotten writing a little high there. So this double integral over T of dP dy dxy duv plus dP dz dzx duv. So all I want to do is verify that I can rewrite this integrand, just the thing sitting inside here, as the derivative with respect to u of p times dx du, or sorry, dx dv, minus the derivative with respect to v of p dx du, and then du dv. Now, we're not going to fully go through this, but let me just explain how you would do this, okay? You would need to write out what the derivative with respect to u of this term is, okay? So just to give you an idea, you would say, okay, I need to calculate d du of p times dx du. Well, that's a product of two things, and notice that p depends on u, okay? So I have to use the product rule here, okay? So I would need to say, okay, this is dp du times dx du plus p times d squared x, sorry, this is a dv, du dv. Okay? And then I would go through and say, well, what is this? Well, now I have to use the chain rule, okay? But u appears in each of these terms. So to calculate dp du, I would apply the chain rule, and I would say, well, I need to take the derivative of p with respect to the first variable. I'll call that like dp dx times dx du plus dp dy times dy du plus the derivative of p with respect to z times dz du. And now I'm going to plug that in there. Okay. Then I'm going to do the same thing here, and then I'm going to combine all these terms, and then I'm going to rewrite some of them as determinants, right? It's a tedious calculation, but it's something you can verify. Okay, so we're really just saying here that I can actually rewrite all of this messiness as this. Okay, and it's not immediately clear that that's any better. It turns out to be more helpful, but it is something we can do. It's just a tedious sort of derivative calculation to check that those are equal to one another. All right, but again, hopefully there's some advantage. Okay, so let's go to the next steps. We're going to sort of flip to some new slides. Let me erase this. All right, so now in the next step, we actually want to apply Green's theorem to that double integral we were just looking at. Okay, so if you sort of just to remind ourselves, sort of, big picture, what we've been doing, right? We said we started with this double integral, or sorry, the surface integral of minus dp dy dx dy dx wedge dy plus dp dz of dz dx. Okay, so we started with this. Okay, and so far what we've done is we've shown that that is equivalent to the double integral of d du of p dx dv minus d dv p dx du. And then this is duv, or du dv. This is over region T. All right. Now what we want to do is we want to apply Green's theorem to this integral. Because now notice, right, this is just a double integral in the plane. Okay. And what I notice is that this is essentially, I can think of this, excuse me, I can think of this as the, right, what does Green's theorem say? It says the double integral over T of dq dx minus dp dy dxy is equal to the line integral over c of p dx plus q dy. All right, so I've got to understand here, let's see, I think I want to think about my u as my x, right? So that means this is going to be like my q, and this is going to be like my p. But again, I can't exactly call these p and q because in this proof they already have meanings, okay? But what it tells me is that I can rewrite this via Green's theorem as the line integral over what? Over the boundary of T, that's what we call capital gamma. Get a little, write a little smaller here. This is the line integral over gamma. That bleeds together too much. The line integral over capital gamma of P dx. So that's rho, or P, sorry, dx du. And then this is du. So it's P dx plus Q, which is just going to be P dx dv, and then dv. Yeah. We're again, we're traversing gamma here in the counterclockwise direction. All right. Now, if we sort of finally parameterize this curve gamma, okay, so I'm going to capitalize this curve capital gamma with the function lowercase gamma. So lowercase gamma is going to parameterize capital gamma on AB. And then I'm going to set alpha of t to be r of gamma of t. So again, the idea is you're over here in parameter space. Here's gamma. You capital gamma. You parameterize it by the function lowercase gamma. But then you map that via this over to the surface, right? And so, right now, r of gamma of t is giving you r of gamma of t here is now giving you the boundary of this surface. Okay. If I do that, okay, then if I write everything out in its sort of parametric representation, if I think about what this ought to be, then I would have that the If I just write out in terms of this parameterization what all of these things should be, I get precisely that this comes back to be the integral over C, because again, now this is getting mapped to C of P dx, which is exactly what I want to show. Okay, so now I've worked all the way through, right, to show that this is equal to this, is equal to this, is equal to this, is equal to this. And so now what I finally have is equality of these two pieces, which was part one of what I wanted to prove. Okay. Now, you prove part two and part three in very similar ways. You do have to be very careful about exactly, where all the x's and y's and z's go. You have to set up this lowercase p function has to be slightly different, but you can do it. It's exactly the same proof. Now, in sort of spirit, what you are doing is you're taking Stokes's theorem, which is fundamentally about something in 3 dimensions, and you're breaking up into parts, each of which are inherently 2-dimensional problems, right? And so because they're now 2-dimensional, you're really sort of breaking Stokes' theorem up into 3 theorems that are each about sort of projecting things down into these lower dimensional planes, either the xy plane, the yz plane, or the xz plane. And there you can apply the special case of Green's theorem, which then helps you recover Stokes' theorem. Okay. Now, again, in a Calc 3 course, if you're ever teaching a Calc 3 course, you're going to spend a lot of time just using Stokes' theorem to calculate things. What we want to focus on here, again, is the fundamentals of why Stokes' theorem is true. We want to understand that Green's theorem is really just a corollary of Stokes' theorem. But in terms of proving it, it's actually easier to prove Green's theorem first, and then use Green's theorem to prove Stokes' theorem. Okay. So we will conclude our video here. In the next video, we'll look at the last of the major theorems from multivariable calculus, which is the divergence theorem.